Hi everyone, my name is Ibrahim and in this video I'll walk you through task 3, which is the full data preparation and pre-processing pipeline. I'll go through every single operator, explain what it does, why we used it and what it achieved. So let's start from the beginning. So before we start everything, task 3 or the process, we first keep this operator, which is considered the opening, the read CSV operator. So when we click on it, we click on import configuration wizard. This helps us in to keep our raw data. This is our raw data. So we start by loading the Washington State electric vehicle population dataset using the read CSV operator. When it loads in, we have 257,635 rows and 17 columns. That's a large government registration dataset. And looking at it through, you can already see some problems, zeros where they shouldn't be, for example here, and missing values in some columns, and location data stored as text rather than actual coordinates. So the entire purpose of task 3 is to fix all of that. So let's keep the dataset. We kept it, so now we can start our process. So the first step or the first operator is the remove duplicates operator. So in this we set it to check for duplicates based on the DOL vehicle ID column. That's the unique identifier assigned to each registered vehicle by the Washington State Department of Licensing. Every vehicle should appear exactly once. In our case, no duplicates were found, which confirms the integrity of the government source. But it's still important to run this check. If duplicates existed and we didn't remove them, our model would see the same vehicle multiple times and give it more weight than it deserves. So this is our first step, keeping the remove duplicates operator. Now moving on to the next operator, the filters example operator. This operator keeps only rows that meet a condition, or in our case, removes rows that don't. We set it to remove any row where county or city is null, meaning the location data is completely missing. Only 8 rows had this problem, so the impact on the dataset is minimal. We chose to delete them entirely rather than impute because county and city are geographic identifiers. You simply cannot guess which county a vehicle belongs to. So replacing them with a placeholder would be meaningless and potentially misleading to the model. So this is what we did in the second operator. Now moving on to the third operator, which is the declare missing value operator. Now this is one of the most important operators in the pipeline. Declare missing value reflags specific values as true missing values. We applied it to 2 columns, electric range and base MSRP, with the flagged value set to 0. As I showed you earlier in the read CSV when I kept the raw dataset, I showed you that the base MSRP had a lot of zeros. So this is why we're using declare missing value. And the reason that zero is in both these columns doesn't actually mean 0. An electric range of 0 doesn't mean the vehicle has no battery. It means the range wasn't recorded or wasn't applicable at the time of registration. Same for base MSRP. 98.7% of all rows have a 0, which makes it obvious that 0 here means the data simply wasn't collected, not that the vehicle cost nothing. Without this step, the next operator would have no idea these zeros are invalid and would treat them as genuine data. By declaring them missing first, we're telling RapidMiner to treat them as black entries that need to be handled properly. Okay, now moving on to our next operator, which is the replace missing values operator. So now with the zeros properly flagged as missing, replace missing values, fill them in. We applied it to 2 columns. For electric range, we replace missing values with the column average, but importantly, this is the average of all non-missing, non-zero values. That average is 111.2 miles. So all 157,670 zeros in electric range were replaced with 111.2 miles. If you look at the histogram after cleaning, you'll see a large spike at exactly that value, which is exactly what we expect. This tells us that the imputation worked correctly. So for legislative district, which had 597 genuine null values, we also imputed with the column average. Legislative district is a numeric code between 1 and 49 representing Washington state political districts. The average gives a reasonable central value when the district is unknown. So we chose the average rather than median or mode because both columns are numeric and continuous. So the mean is the standard imputation method for this data type. And this is what we did. As you can see here, this is what I talked about. You can see it here, and this is what we did, replace with average. Okay, so now moving on to our next operator, which is the select attributes operator. So select attributes remove columns we don't need. So we removed 3. First, we remove the VIN, which is the vehicle identification number. Every vehicle has a completely unique VIN, so it adds 0 predictive value. The model cannot learn anything from an identifier that changes for every single row. Now the second attribute we remove, the base MSRP. We declared its zeros as missing earlier, but the column still has 98.7% of values as 0 even after that declaration. There simply isn't enough real data in this column to be useful. So we remove the entire column rather than carrying it forward as mostly missing. And for the third and last, the 2020 census tract. This is an extremely granular geographic identifier with thousands of different codes for tiny sub-regions. Keeping it would cause severe overfitting. The model would memorize specific census tracts rather than learning general patterns. So we already have county and city for geographic context, which is more than sufficient. After this step, we're down to 14 relevant attributes. And as you can see here, these are the columns that we decided that we don't need, so hence we removed them. Now moving on to the set role, operator. So the set role operator changes the designated role of an attribute. We set DOL vehicle ID to the ID role. This tells RapidMiner that this column is purely an identifier. It should not be used as a predictive feature by any model, but it should be kept attached to each row for traceability. If we ever need to look up a specific vehicle in the original dataset, the DOL vehicle ID makes that possible without using it to train models. And this is what we did. So what I said, basically, I implemented it here, as you can see here. Okay, so the next operators, operators 7, 8, and 9, they replace, split, and rename. So we use the next 3 operators to make them work together to parse the vehicle location column. So the raw data stores location as text in WKT format. It looks like, for example, minus 122.3 and 47.6. Like this is how this is how the location was kept in the raw data. So that's basically like keeping longitude and latitude. So instead of keeping it in a text string, we changed it to a numeric feature so that it will become useful. So the replace operator uses a regular expression to strip out the word point and the surrounding brackets, leaving just the two coordinates numbers separated by a space, which is the longitude and latitude. And for the split operator, so the split operator takes the two numbers separated by a space and divides them into two separate columns, one for longitude value and one for latitude value. That way it's much more easier and useful to use in, for example, real world scenarios or real world applications. And finally, the rename gives the two new columns proper names, longitude and latitude. What started as a looked up text string called vehicle location is now two clean, usable numeric geographic features. This is feature engineering, creating useful new inputs from raw text data. And this is what we did in these three operators. Now moving on to the next operator, which is guess types. After all the transformations, replacing, splitting and renaming, the data types of some columns may have been disrupted or left as the wrong type. Guess types automatically scans every attribute and corrects its data type. It identifies which columns should be integers, which should be real numbers, and which should be nominal categories. This matters because many downstream operators in RapidMiner require correctly typed data to function properly. Without this step, some operators might refuse to run or silently produce incorrect results. So this is considered a pretty important operator in our process. Now moving on to our next operator, the sample stratified operator. The final operator in the main pipeline is this, the sample stratified. This reduces the dataset from 257,635 rows down to 50,000. We have to be careful here. We are not taking the first 50,000 rows or picking randomly. Stratified sampling means the sample preserves the class distribution of the target variable. In our dataset, approximately 79.6% of vehicles are BEVs and 20.4% are PHEVs. Stratified sampling guarantees that 50,000 rows sample maintains exactly that same 80 to 20 ratio. If we had used random sampling instead, there's a risk that the minority PHEV class could be underrepresented, which would bias our classification model toward predicting BEV. So 50,000 rows is large enough to be statistically representative while being manageable for model training and evaluation. So now we're kind of reaching the end of our process. We have the PCA. We'll now be talking about the PCA branch. So below the main cleaning pipeline, you can see a separate analysis branch. After guess types, a multiply operator splits the data into two streams. One continues to sample stratified as normal. The other goes into the PCA chain for dimensionality reduction analysis. So the PCA, there are steps to it. So the first step we took in the PCA is we kept the replace missing values. So before PCA can run, every value in the numeric columns must be present. PCA cannot handle missing values. This second replace missing values operator ensures any remaining nulls in the numeric attributes are filled in using column averages before the data enters PCA. This is our first step. The second step in PCA is the select attributes. So PCA can only operate on numeric attributes. This select attributes operator keeps only the 6 numeric columns: model year, electric range, legislative district, DOL, vehicle ID, longitude, and latitude. All categorical columns such as make, model, county, and city are excluded. PCA would not know what to do with text text values, which is why we only kept these 6 numeric columns. Now for the third and last step in the PCA is the PCA operator. The PCA operator runs a principal component analysis on the 6 numeric features. The variance threshold is set to 0.95, meaning PCA will automatically select however many components are needed to explain at least 95% of the total variance. We didn't hard code a fixed number of components, we let the data decide. Now that we finished our process, we can now simply run the process, and it will give us the results. So here are the results. So for the PCA results, here are the results. So the PC1 has a standard deviation of 2535.923 and explains 99.9% of total variance on its own. We only needed one component to exceed the 95% threshold out of a possible 6. And the cumulative variance, for the cumulative variance chart makes it visually obvious. The line jumps straight to 1.0 at PC1 and stays completely flat. So every additional component adds essentially nothing. And this is what the cumulative variance chart tells us. Now we go to the example set PCA. So in the output example set, all 6 numeric columns have been replaced by a single column called PC1. That's a dramatic dimensionality reduction from 6 dimensions down to 1. What does this tell us? You may ask yourself. Well, to answer your question, electric range has a scale in the hundreds of miles, while all other numeric features are much smaller. It naturally dominates the variance calculation and captures almost all the information in the numeric feature space. This confirms electric range as the most important numeric feature, exactly what we see in the decision tree root split in task 4, which will be shown to you later. We did not use the PCA output for model building. PCA transforms the original features into abstract mathematical components. You can no longer say electric range greater than 72.5 because that interpretability is gone. It would also eliminate all categorical features which carry real predictive value for edge cases. PCA was used here purely for exploration to confirm electric range dominates. The original cleaned features go forward into task 4, which also I'll be showing you later. So the summary, task 3 summary, so that's all 11. So that's all 11 operators in task 3. The pipeline takes 257,635 messy rows with zeros, null, text coordinates, and redundant columns, and produces a clean, balanced, properly typed 50,000 row dataset ready for model building as you've seen. The PCA confirmed that electric range is the dominant numeric feature. Everything is now set for task 4. Hi everyone, welcome to task 4. So the cleaned 50,000 row dataset from task 3 enters this pipeline, and we build 3 classifications models to predict electric vehicle type, whether it's BEV or PHEV. So I'll go through every single operator in sequence, explain what each one does, and then show you all the results at the end, exactly like what I did in task 3. So now, starting with the process. So in task 4, the first operator I used is the set roll 2. So in set roll 2, this is different from the set roll in task 3, which set DOL vehicle ID as an identifier. Here we're setting electric vehicle type as the label, meaning it's the target variable we want every model to predict. Without setting this role, RapidMiner wouldn't know which column to classify and which columns to use as features. And this is what we did in the first operator. Now moving on to the second operator, which is the split data operator. So the split data divides the data set into three separate partitions using a 70-20-10 split, or as you can see here, 0.7 which is 70%, 0.2 which is 20%, 0.1 which is 10%. This is the split. So partition 1 is 70%, which takes up 35,000 rows. This is the training set. The model sees this data and learns patterns from it. Partition 2 is 20% and it takes 10,000 rows. This is the test set. After training, we evaluate each model here to measure performance on data it hasn't seen. And the last, which is partition 3, is 10% and takes 5,000 rows. This is the validation set. This data is kept completely untouched until the very end. The model never sees it during training or parameter tuning. It gives us a final unbiased check on whether the model genuinely generalized to new set. So we chose 70-20-10 over a simpler 80-20 split like we did in task 3, specifically because having that separate validation partition proves the model aren't just memorizing the test set. Stratified sampling is enabled, so the 80-20 BEV or PHEV class ratios preserved identically across all three partitions, and this is what we did in the second operator, the split data operator. Okay. Now moving on to the third operator, which is multiply 2. Multiply 2 is critical for ensuring a fair comparison between models. It takes partition 1, the training data, and sends identical copies to all three model branches simultaneously. Decision tree, naive bias, and vote ensemble all receive exactly the same 35,000 training rows. Without multiply, we would have to chain the models sequentially and could never guarantee they trained on identical data. Now moving on to our fourth operator, which is the decision tree. So the first model is the decision tree. Let me go through each parameter. So criterion is set to gain ratio. This is more robust than information gain for our 80-20 imbalanced dataset. Information gain tends to favor attributes with many distinct values, so gain ratio normalizes for that, giving a more balanced assessment of which feature actually separates the classes best. So the maximal depth is 10. This limits how many levels deep the tree can grow. A deeper tree would memorize the training data too closely. Every leaf would represent a single training example and the model would fail on new data. Depth 10 gives the tree enough room to learn meaningful patterns without overfitting. Apply pre-pruning is enabled with minimal gain set to 0.01. Pre-pruning stops branches from being created if they don't improve the model by at least 0.01 gain ratio. This prevents the tree from growing useless branches at the end of the structure. Okay, confidence is 0.1. This controls post-training pruning. It removes subtrees that are statistically unlikely to improve generalization on new data. Minimal leaf size is 2. Every leaf node must have at least 2 training examples. This prevents single example leaves, which would be unique to one data point and completely useless for prediction. And this is what we did in the fourth operator or decision tree operator. Now moving on to the next one, which is the which is the apply model decision tree test. Okay, so apply model takes the trained decision tree and applies it to the test partitions. Partition 2. This is where the model makes predictions on data it has never seen before. The output is the test dataset with a new column showing the model's predicted electric vehicle type alongside the actual known values. And this is what we did, or what the fifth operator, the apply model decision tree test, basically do. Now moving on to our sixth operator, which is the performance decision tree test. So the performance operator compares the model's predictions against the actual values in the test set and calculates accuracy, precision, recall, and the confusion matrix. This is our primary measure of decision tree test performance. Okay, now moving on to our next operator. Our next operator, operator 7, is multiply 5. So multiply 5 does the same job as multiply 2, but for the test partition it sends identical copies of partition 2 to all three apply model test operators simultaneously, one for each model. This ensures all three models are tested on exactly the same data. Now moving on to our next operator, operator 8, or the apply model decision tree validation. Okay, now our eighth operator, which is the apply model decision tree validation. This apply model operator applies the trained decision tree to partition 3. So the validation set. This is the completely untouched data that was held back from the very start. The model has never seen it, never been tuned on it, and was never influenced by it in any way. This is the true test of whether the model generalizes. And now moving on to the next operator, operator 9, which is the performance decision tree validation, which is this one. So here, this performance operator measures the decision tree accuracy on the validation set. If validation accuracy is close to test accuracy, it confirms the model generalizes well and is not overfitting. If it had dropped significantly, that would be a warning sign. And this is basically what operator 9, or the performance decision tree validation, basically does. Now moving on to our next operators, operator 10 to 14, which is the naive bias branch. Okay, so the naive bias branch follows exactly the same structure. Naive bias, then connected to apply model test, and connected to performance test, and then apply model validation, and then performance validation. It receives the same training partition from multiply 2 and the same test and validation partitions from the multiple operators. For naive bias parameters, Laplace correction is enabled, which you can see here. It has a check mark. So without it, if the model encounters a feature value during testing that it never saw during training, the probability for that entire class drops to 0, literally breaking the prediction. So Laplace correction adds a small smoothing value to every probability to prevent this. So use kernel is disabled. Kernel density estimation is useful for purely continuous numeric distributions, but our data set simply contains predominantly categorical and integer typed features. So kernel estimation would add unnecessary complexity without any benefits. Okay, sorry. So the apply model and performance operators, which is here the apply and performance operators, work identically to the decision tree branch. Apply the trained model to the partition, then measure accuracy, precision, recall, and the confusion matrix. So this is basically what has been done in operators 10 to 14. Okay, now moving on to our next operators, which are operators 15 to 19, the vote, ensemble, branch. Okay, so the vote ensemble branch also follows the same structure. It receives the training partition from multiply 2 and has the same apply model and performance operators for both test and validation. Okay, so now let me open the vote operator to show you what's on the inside. Okay. The ensemble contains decision tree 2 and naive bias 2 as inner learners, configured with exactly the same parameters as the standalone models. Both are connected to the training input port and both train independently on the same data. So their trained models are passed to the vote output ports. At prediction time, both inner models make their own independent prediction for each vehicle. If both say BEV, the answer is BEV. If both say PHEV, the answer is PHEV. If they disagree, the model with higher confidence wins. The majority vote makes the ensemble more reliable than either model alone. Two independent algorithms checking each other's work. And this is basically what's been done in the vote ensemble branch. Okay. So now for the next operators, which is multiply 3, multiply 4 and multiply 5. These three multiply operators handle the validation partition distribution. So multiply 3 sends partition 3 to the decision tree validation apply model. Multiply 4 sends it to the naive bias validation branch. Multiply 6 sends it to the vote ensemble validation branch, which we talked about. So all three receive identical data, ensuring the final validation comparison is completely fair. So now moving on into the results. Okay, so for the results now. So decision tree results, the 99.73% accuracy on the 51,386 test examples. The confusion matrix shows 41,012 BEVs correctly classified and only 133 BEVs misclassified as PHEV. For PHEVs, 10,374 were correctly identified and only 6 were misclassified as BEV. BEV, recall, reached 99.99% virtually perfect. Now we go to... Okay. So now we go to the decision tree validation performance. So here in the validation results, 99.78% accuracy, which you can see here. The validation accuracy is actually slightly higher than test accuracy, confirming no overfitting. Only one PHEV was misclassified on the entire validation set, as you can see here. Now we go to the what is it? Okay, so now we move on to our tree tab. Now here's the most valuable output. So the decision tree diagram itself, you can see it here. Look at the root node. Electric range greater than 72.5 miles. That single split immediately separates the majority of vehicles. So BEVs consistently have higher battery ranges than PHEVs. This one threshold cleanly separates most of the data set. The second level adds model year and the secondary electric range threshold for borderline cases. The third level uses make, BMW and Land Rover go to PHEV, Mitsubishi and Small go to BEV, and electric and the electric range is the dominant feature, exactly as the PCA analysis in task 3 suggested it would be. So now we go to the results of naive bias, which is right here. So the naive bias test results, it has a 99.60% accuracy, as you can see here. The confusion matrix shows 75 PHEVs misclassified as PEV compared to the decision trees 6. This is expected. Naive bias assumes all features are statistically independent of each other, which is violated here because electric range and electric vehicle type are strongly correlated. Despite this violated assumption, 99.60 is still an excellent performance. And now we go to the naive bias validation. Where is it? Performance. Oh, sorry, my bad. I meant here. You can see the results of the naive bias, but on here, in the validation performance, it gets a 99.64% accuracy. This is consistent with test accuracy, confirming no overfitting. And now I will show you the results of the vote ensemble. Okay, now for the vote ensemble performance. So vote ensemble test results, it gets a 99.73% accuracy, as you can see here, identical to the decision tree on the test set, which you can see here. Both are similar. So the confusion matrix shows the same 6 PHEV misclassification on the data on the test data. So okay, now when we go to the ensemble validation performance, the validation has a 99.79% accuracy, which is the highest of all 3 models. And look at the confusion matrix, 0 PHEV misclassifications. Not a single PHEV was incorrectly labeled as BEV on the completely unseen validation set. That's the ensemble correcting individual model errors through consensus between 2 independent algorithms. So now that I've shown you all the operators that I've used, why did I use them, what did they achieve, the results, everything. Now I can give you like the conclusion or the summary. So now to summarize task 4, there are 3 models, all exceeding 99% accuracy on both test and validation sets. The decision tree revealed that electric range greater than 72.5 is the single most important classification feature, and the naive bias provide a strong probabilistic baseline. The vote ensemble achieved the highest validation accuracy of 99.79, as you can see here, with 0 PHEV misclassification on the final unseen data. So the consistency between test and validation accuracy across all 3 models confirms no overfitting occurred in any of them. The vote ensemble is recommended. It achieves the highest generalization accuracy and the most reliable predictions on completely new data. That's exactly what the manufacturer needs when making production decisions based on these results. And this is it for task 3 and task 4. Thank you everyone for listening, and bye bye.